In this video, I want to explore a little bit more in detail how we get the figure which tells us what is the sensitivity of a receiver. There are different methods for measuring sensitivity of receivers, the ones that I reckon are widely used, and also the ones that I have here in my test set, are the SINAD, as you can see here, and the signal to noise ratio. The difference between the two is that the SINAD also takes account of the distortion, because the distortion will impair the sensitivity of the receiver, the readability of a signal, let's put it that way. If we look here on the Marconi, sorry for the cables, actually I can get rid of this one here and this one as well. If we look here on how to set up, we look for topics, we can ask the Marconi about distortion and signal to noise and SINAD. And here Marconi is giving us some information. They say, okay, they explain how it works with this testing instrument. And here it says the measurements of AF harmonic distortion and noise relative to the signal are as follows, and it gives us three formulas. Distortion factor has a percentage, signal to noise ratio, the ratio expressed in dB. As you can see, there is the signal, the noise, and the distortion. But the SINAD, because when we inject a signal into the receiver, there will be it will appear the signal over the noise, but the signal will have its own distortion as well, possibly, no? A certain amount of distortion. It can be very pure, but it can be distorted as well. So when we measure this voltage, we take account of the final result of these three elements, and we compare with the noise, with just the noise. So that is removing the signal with its distortion, and we are left with the noise. Whereas in the SINAD, we compare once again the three elements, but we will compare those elements to the noise and the distortion as well. And doing that is the instrument will just notch out the fundamental frequency of the signal, and will leave the noise and the harmonics making up the distortion of the signal, and that's in dB. So as you can see, it's a 20 log the voltage, 20 log, so that's in voltages. Yeah, that's it. So if we go here on AF test, go here on AF test. Well, actually, no, before we do that, I will check this. Let me go back again. I will check this ratio, the signal to noise ratio, and to do that I will use this formula and I will attempt to measure the voltage on the upper side of the fraction, and then we remove the signal with this distortion and we will measure the voltage level of the noise. We will then calculate this fraction, do the logarithm, the log base 10 of this, and multiply by 20, and we will get a number in dB. So to do that, I'm gonna use my Rakaldana 9300F, which is an analog instrument which measures voltage levels from 5 Hz to 20 MHz with a good degree of accuracy. And yeah, so let's measure that, okay? So we are sending to it the audio spectrum coming out from this scanner once again. We are on amplitude modulation on a frequency here in the aeronautical band 123 decimal. It could be whatever frequency. As you can see, the lamp here means that it's receiving. The squelch is open. In fact, I'm sending a carrier. As you can see here, let me get the brightness a bit down. I'm sending a carrier on that frequency at 0.85 microvolts, which is about minus 108 dBm. So let's and the audio tone that I'm sending is 1 kilohertz at 30% depth. So I will switch on the modulation now. Okay, modulation is on, and if you can hear it. Okay, and let's look at the voltage. Okay, so the voltage, we are on a scale of 300 millivolts full scale, so we are on the bottom scale. Let me get some light. On the bottom scale, and we're looking at 240 roughly, okay? 240 millivolts. Okay, so let's write that down. Let's write that down here. So the fraction, we've got the signal, we've got the noise, and we've got the distortion over the noise. And on this side we measured 240 millivolts. I want to measure now just the noise, so to do that I will switch off the audio tone and we go and read the voltage again, a lower scale, 100 millivolt upper scale, and we are looking at 66 millivolts. Okay, they're about 66 millivolts. Okay, so let's write that down. 66 millivolts. Okay, let's so I wrote again the entire formula, and let's do the math now with the help of a calculator as well, of course. We can do it separately, but with this calculator I can, if I remember correctly, I can do everything in one row. 20 times log, that's log on base 10 of 240 divided by 66, and the result will be a number which is we take it in dB, and will be the ratio 11.2. So the signal to noise ratio in this particular case gave us 11.2 dB. So this is our how can I say well usually when we read the specs, as far as I know, the signal to noise ratio has a threshold which by definition has been established to be 10 dB, where the SINAD has been established to be 12 dB. Okay, so 11.2, we're a bit higher than 10 dB. So if we see what is the voltage level of the signal that I have injected to get this ratio, just go here and read the level. It's 0.85 microvolts. So what does it mean? That to get 10 dB of ratio, we can lower down this figure, and we could do the math backwards to have this ratio to be 10, okay, with the exponential. Okay, so doing some math calculations, it turns out that if we lower the level of the incoming signal into the receiver, so to read, instead of 240, about 210 over 66. This, applying the formula 20 log of this, will give us 10 dB. Okay, so let's do it. Let's switch the modulation on, and let's go to the voltage millivolt again. Let's go for 210. So I will lower the level. We're about there, around 210 millivolts. And what's the level now? What's the level now? It's 750 nanovolts, or 0.75 microvolts. Yeah. So this means that a sensitivity of the radio for a signal, let's put it this way, signal to noise of 10 dB with 1 kilohertz tone and 30% depth will be, sensitivity will be 0.75 microvolt, which corresponds to minus 109.5 dBm. Okay, this is the signal to noise ratio figure. Now I will try calculate also the SINAD for 12 dB this time. With this, well, actually no. Let me do this first. Let me double check. This is what we found with the formula and with the measuring the voltage level from this meter. Well, first of all, you can notice that when I switch on the signal, the modulating signal, I'm about here, because this instrument has a dB scale on the bottom. You can see that let's say we are just under -1, okay? If I switch off the signal, for 10 dB ratio, we should end up -1, -10 is -11. And this is where we end up, in fact. If we change scale, it's a 10 dB difference. So we should come back to the same point. And as you can see, that is verified. So it's also, if you have this instrument, instead of doing the math, you could just make it easier. Just measure whatever, you know, put the volume, okay, of the receiver, so that you get into a certain point, you know. For example, yeah, let's go on 0, for example, okay. Okay, we are about at 0. And yeah, change scale. So we want a 10 dB ratio, so just change the scale for a 10 dB delta. Switch on the modulating signal on the generator and adjust the level. And adjust the level until you find the same spot, about 0. And there we are. And look where are we? Look where I stopped. So I was tuning the knob for the level, not looking at here, but looking at the millivolt meter. So in fact we end up with the same result. 7.74, 0.75 is about the same. Okay, let's see what now the Marconi says, because the Marconi can measure the signal to noise ratio. Let me set it up. Okay, now the audio has been hooked up to the AF input port, and the signal to noise ratio has been enabled. And look what the Marconi says. The level is 7.75 microvolts. Nothing's changed. Signal to noise 9.9, 9.8. So we had basically thanks to the instrument, we had the same result. We get to the same result instead of doing the math, which by the way is quite simple. Just apply a formula with 2 numbers. We got the same result. Yeah, so let's have a look now on FM to a SINAD ratio. Okay, so to do that, I changed to the 2 meter handband, 145 megahertz on FM, and we are here set at 145 megahertz, 1 kilohertz tone with deviation at 3 kilohertz. Now, modulation is on. You can hear the tone if I bring the volume up, and we can see the tone here. Now what happens is that I'll show you one thing. If I increase the volume here on the scanner, we will see what happens. We can see that the harmonic appears. That means that the signal now is not pure anymore, but it's distorted. Okay, so I'll bring the volume back down until we see those harmonic disappear. And we check the SINAD now. SINAD measurement is on. This is the value. And what we look for is 12 dB ratio. 12 dB ratio. So I'm gonna reduce the level here until we reach a ratio of 12 dB. Let me check one thing first. Yeah, okay. So yeah, we want to stay about here. 12 dB. The full scale here is 18 dB. So yeah, we are about there. We're about there. It's fluctuating a bit, but it's about 12 dB. And this is how it sounds like. And if I switch it on and off, you can hear the signal in between the noise. Now, if we want to establish the spec for this receiver and see and write the sensitivity on this band, we will say that for 12 dB SINAD, let me get the volume away. 12 dB SINAD with 1 kilohertz and 3 kilohertz deviation. Sensitivity will be about 0.25 microvolts. 245, let's call it 0.25. That's it. That's how we define the SINAD. Now, I cannot do the same thing with the voltmeter, because in the equation where we have, for the SINAD equation, we will have signal plus noise plus distortion over noise and distortion. Now if I remove the signal, I can measure this, but if I remove the signal, I'm not left with noise plus distortion, I'm just left with noise. So it will be back to the signal noise ratio. To take account of distortion, I should actually remove just the fundamental from this term here, and this is what the instrument does. Yeah, so this is telling us as well that if the distortion is negligible, we end up with a SINAD being basically a signal to noise ratio. And furthermore, if the signal is much bigger than the noise, we can take out both. We can say that the term reduces to signal over noise. Now, before I close the video, I put up a little experiment using the function generator, which is 2 channels. On channel 1, I'm generating a pure sine signal, and on channel number 2 I'm generating some noise. Okay, the channels are already on, and this is the result. You can hear the noise and the signal and the tone. Now, the SINAD ratio is about 12 dB. Now if I go and switch on some harmonic to it, I'm effectively distorting the signal. And I switched on the second harmonic, as you can see here, then up to 40 millivolts, and we can see it here appearing. And what we can see is that the SINAD got worse, 10.4. And as I increase the level of the second harmonic, we should see the SINAD going down. Let me do that. You see the harmonic now has gone up, and the SINAD's got worse. And I could do that with other harmonics. In fact, I could go to a square wave 1 kilohertz, which is basically has a content of infinite harmonics. So let's see what happens. Now we've got all the harmonics, and we see the SINAD has gotten worse. So as you can see, the SINAD is reflecting also the distortion content, as we know by the formula. And back to sine. Yeah, just a little experiment to show the behavior of this on this subject. Well, I'm not a teacher, obviously. I'm just a hobbyist. So, in doing so, I'm also playing around with my instruments, having fun and learning things as well. So that's all. Thank you for watching. Bye now. 7 to 3.